Can you see the slide?
Yes, sir.
Okay, let's start without further delay. So we will continue from our discussion in the last class. In the last class, we discussed different cache organizations. When you are dealing with cache, you have to remember that we will deal with blocks with the kind of chunks of data which are called blocks or cache lines. I prefer the term block, but anyways, cache line is also very popular. A cache deals with chunks of data in terms of blocks. Okay, so when it fetches data from memory, it will fetch data in terms of multiples of blocks. Now we were discussing different methods of mapping memory addresses to cache indexes. Why were different methods are necessary? First of all, why mapping is an important concept in the context of puffs, because in the context of cache memory, because cache memory are very small compared to the main memory. As a result, in general, it is a many-to-one mapping. The many-to-one mapping creates collisions, and the performance of the cache in terms of the number of hits and misses when you have a sequence of addresses depend largely on two factors. One is this mapping mechanism, and the second is, of course, the sequence of addresses, the block addresses that you are dealing with. If you are lucky, your number of misses might be less, but if you are not that lucky, the number of misses can be very high. We discussed three different techniques. Okay, actually two different techniques, but we will consider for simplicity three different techniques. One is called a direct mapped cache, where essentially the mapping, the index finding mechanism is very simple. You take the block address and you calculate the modulo, the remainder, the number of blocks in the cache. Okay, and if your blocks is a multiple words and number of blocks is usually a power of 2, the indexes are simply certain number of least significant bits. That depends on how many blocks you have in your cache memory. Okay, so very simple mechanism to fully resolve the address, because there is ambiguity of this many-to-one mapping. You have a concept called cache tag. Along with that, you have a further valid invalid bit, valid not valid bit, which tells whether the cache entry can be trusted or not. So overall, the content of the cache, other than this detection hardware, this equality comparator, ending, etc., all this logic, overall by cache we mean the portion of memory, the portion that stores the data and the tag and the valid bit. Okay, so this the size of that can be calculated. It is a function of the block size, of course, and how many blocks are being supported, etc., etc. In your textbook, there are closed form formula of the size of caches with respect to these parameters. However, you do not need to memorize such formula by heart. If you logically understand how cache is organized, you can easily work out the size of a cache. So in this example, again, the word size is the block size is 1 word. So directly by taking the word address, 32-bit word address, you could figure out everything very easily. All the time it is not easy. Sometimes, for example, if there are 4 word blocks, then your word address indexes have to be modified accordingly, and the offset also has to be modified accordingly. Basically, the idea is that you push the start considering one block as one word, okay, large word, and push as many bits as possible as needed to the offset field. Then you can figure out from the index how many blocks you are supporting. Okay, 64 blocks being supported means 6 bits, and then the remaining bits are tags. The problem with this single this direct map cache is that, well, you are kind of you don't have much flexibility. So people go for other cache organizations. One is called a set associative cache organization, where you provide certain amount of liberty. Okay. Now the cache is organized in a number of sets, and each set can contain multiple blocks. Okay. If a set contains n blocks, this is called a n-way set associative cache. In an n-way set associative cache, every block or every memory block has n options of coming and sitting inside the set. Okay, so first, now the memory block address would be mapped to a set. Inside the set, if one position is left, you go and sit in that position. If both the positions are left, you sit at any place, and if one position is left, you go and sit there. An extreme version of this is a fully associative cache, because in a fully associative cache, a memory block can come and sit anywhere inside the cache. Okay, it can be mapped to any cache block. So you are giving full freedom. And I compared these different schemes with the schemes of students sitting in an exam hall. In a direct map cache, the exact roll number of the student is mentioned, and the student has no option but to go and sit there. In a set associative cache, which is kind of the system followed in the exam when you go to write the central exam papers in say IIT Kharagpur, centrally organized exam papers, you are given slots. So maybe there are 4 slots, A, B, C, and D, because 4 papers are happening in the same time slot. You are given an option that you are assigned 1 slot, and you have the option of sitting in any available seat of that slot, which means any A slot seat you can go and sit. This is the basically the set associative scheme. Okay, if there are 20 available seats for each slot in the hall, that will be a 20-way set associative scheme. Okay. A fully associative scheme is a scheme where the student can go and sit anywhere. There is no restriction. Okay, anywhere you go and sit. Okay, in the exam hall, there is absolutely no restriction. So that is a fully associative cache. The problem with the fully associative cache, although it gives maximum freedom and it seems really attractive, the problem with that is the hardware design becomes very complicated. Why the hardware design becomes very complicated? Because now you have to compare, you have to search in all the cache locations, where is my data in parallel, and you have to return the result of the search in 1 clock cycle. Okay, so this type of search are usually performed with special type of memory hardware called content addressable memory, or CAM. This CAM is a type of, looks a little bit like SRAM, but it is more complicated than SRAM. A CAM can have up to 10 transistors, and SRAM's bit has 6. I mean, to hold 1 bit in SRAM, you require 6 transistors, whereas a CAM can have 10 transistors. So it is more complicated, more power hungry, but it is faster. In a set associative cache, the problem is not fully solved, because you still need to search in multiple locations parallelly. However, the search is restricted to the single set. So if your set contains only 2 entries, so it's a 2-way set associative cache, you search in only 2 locations. Okay, and in a direct map cache search is very trivial. You just look at the address bits of the block address, and you can directly index into the correct location. So direct map is very simple but inefficient in terms of hit miss patterns. Set associative is fully associative is extremely good, very efficient, gives you very high performance with respect to hit miss patterns, but it is not very practical for large caches. Set associative is kind of the optimal engineering trade-off that is very common. It is extremely popular and it gives reasonable hit miss ratio with manageable hardware overhead. Some experiments have been done that do we improve the performance if the number of entries in each set, that is this n-way set associative caches, the value of n increases. Well, up to say 4-way set associative, it increases, the hit miss ratio decreases. But beyond that, there is kind of Amdahl's law type of law of diminishing return sets in, where it becomes more and more difficult to implement the cache, but at the same time you do not get sufficient improvement in the miss ratio. So it's not worth it actually. Some examples were given where we found that fully associative cache actually is the best option. Just remember one thing, that in direct map cache you are thinking of the cache index, and in the set associative cache you are thinking of the set index. The cache index basically becomes the set index. How can you find the set index? It can be found by the block address modulo number of sets. Okay, remember that. When a decision has to be taken that among the multiple entries in a single set, which one has to be replaced, the cache follows a least recently used principle. A least recently used principle is a principle which says that do not replace the one which cache block, or do not touch the cache block which has been accessed recently. You rather replace the cache block which has been which kind of came into play least recently, so long time back. This long time back is a very subjective statement. It can even be like the last cache access and the last to last cache access, even like that. If you have to compare between them, you select the last to last. This is a very simple principle. The LRU is reasonably easy to implement in hardware. Remember, these things are implemented in hardware. Okay, there is no software that can perform these things. So everything, the entire cache mechanism is hardware. Extremely efficient, fast circuits. So it is very difficult to actually design fast cache memory. Of course, processors have done. So 4-way set associative cache is very, very common. An example of a 4-way set associative cache with 256 sets and total 1024 blocks in the cache is given. Here every block is one word, so directly the word address is taken. The index is given by 8-bit field. The tag is the remaining 22-bit field, and there is a 2-bit word address, word offset. Now your search happens in parallel in 4 locations. Okay, because this is a 4-way set associative cache. In 4 locations, when the search happens, and when one of the locations, if there is a hit, that word has to be sent out. So there is a multiplexer mechanism which actually tells which among these 4 locations the word was found. Okay. So you can understand that if it is an 8-way set associative cache, in that case you will require 8 such logical blocks of the cache, and then the search has to be in parallel in 8 places, and there will be 8-to-1 multiplexer, etc., etc. Now there are 3 types of misses in cache. One is called a compulsory miss, which happens when you access a data for the first time. There is no way to avoid this miss. That is a mandatory or compulsory miss. The capacity miss is something where due to the relatively small cache size, repeatedly necessary blocks which are to be accessed in near future are getting evicted. Okay, they are again being brought back, again getting evicted because the cache size is small. And the conflict miss is related to the capacity miss, that there is empty space in the cache on a whole, but still misses are happening. This can happen in a null fully associative cache and due to competition for entries in a set. Okay, and it would not occur in a fully associative cache of the same total size. Because there are empty spaces, so block could have gone and sat anywhere. So what are the design trade-offs for a cache? Will you increase the cache size? It will decrease the capacity miss, but it may increase the access time, because as you increase the cache size, all the circuitry that are there, those become more and more complicated. More searches have to be performed, and the cache might become slower. The electronic circuitry might become slower. Will you increase the associativity? It will decrease the conflict misses, but again might increase access time, because as I said, that as associativity increases and the cache start becoming more and more towards fully associative cache, the searching mechanism must happen in parallel across all the blocks. One comment is the searching mechanism shown here, where you have a comparator, 4 comparators in parallel, is not the way probably searching mechanism would happen. This is a logically correct diagram. The logical operation that is happening is this, that there is a logical 4-way parallel comparison and then an ANDing, and there is a logical ORing of the results. Remember that the last hit is now an ORing of the 4 results. Any one of them hit in the set, that's, I mean, any one of them hit is the value has been found. Okay, so it's a logical OR. However, in a real cache, this circuitry would probably be implemented in a different, more optimized way, not by directly straightforward this comparison and ANDing and ORing mechanism. Okay, because if this is the case, then your ORing mechanism and the multiplexers, these will become keep on becoming bulkier as you keep on increasing the associativity. Okay, and the hit generation, the decision that a hit has happened is now being generated by a 4-input OR gate. Okay, if you increase the associativity logically to say 8, logically it will be generated by 8-input OR gate, which are very slow kind of, which are very slow circuit. So it will not happen in this way. There are other alternative faster circuits to perform this type of parallel searches more efficient. Then what about increasing the block size? Well, compulsory misses might decrease because you are bringing in larger amounts of data at one go, so that you probably need not go to the memory again and again to bring the next block of data, etc. But it will increase the miss penalty, because remember, although the cache deals with blocks, the memory necessarily does not deal with blocks. The memory, the size of chunk of data that you can read from memory at one go, is not necessarily a cache block. So this is a very important thing to understand. Your cache reads data in terms of large chunks. The memory does not deliver data to the cache in such large chunks. And finally, the cache does not, the processor cannot handle such large chunks at one go. It usually reads only one word at a time from the cache. So try to understand there is a disparity in the sizes of chunks of data that are handled by memory, by cache, and by the processor. So to recall, we did have a look at different memory bus widths. Let me go back a little bit. Notice the one word cache organization, one word wide memory organization. In this, the cache block size is 1. Okay, so it is, I mean, whether cache block size is 1 or not is different. The memory supply the cache with only one word at a time. Something else also. So if the block size, the memory will supply the cache in terms of one word per cycle. Processor always reads one word at a time from the cache. This is a very important thing to understand. Okay, the processor, suddenly the instructions cannot become magical that you are going to read in more than one word at a time from the cache. Your instructions are still load and store, which deal with exactly one word at a time per instruction. So notice that the width of the connection between the processor and the cache in all the three diagrams is constant. It is always one word. Second, what about a wide memory organization? In a wide memory organization, which is the middle option, option B, maybe the memory can transform 4 words at a time to the cache. And if the cache block is 2 power 10 words, it will take 256 cycles, bus cycles, not clock cycles. Okay, 256 bus cycles to read in one word, one block from memory. The bus cycle and the processor clock cycle are different. The bus cycle is typically slower than the bus is out. Remember, the bus is located outside the processor. Okay, so it runs at a slower speed. The moment you take electrical signals outside the processor, they run at slower speed. Okay, maybe some hundreds of megahertz or something. Now, the memory can supply maybe four words at a time to the cache, maybe. Okay, and then it is more efficient, but still the processor only reads in one word at a time from the cache. Okay, so there is a multiplexer mechanism which from the block of these 4 words selects the correct word and sends it to the processor. Finally, it is an interleaved memory organization where now you have 4 different memory banks. These memory banks are logically or physically separate blocks, modules of memory. They can either be in the same chip, logically 4 different modules, or they can be completely 4 different DRAM chips. Okay, they are now connected to the cache, but they can only supply one word at a time per to the cache. Okay, so the bus width is kind of 1 word, and the processor, as usual, takes only 1 word from the cache. But now it is interleaved. Interleaved means that data transaction between the cache and the memory can happen. The memory modules can happen one word at a time, but with the 4 different modules. Then this cache performance measure, CPI and AMAT are very important. We have discussed this. Now, till now, all our one thing is in the replacement policy in set associative, I mentioned LRU. It has been interestingly found that random replacement also gives approximately the same performance as LRU for high associativity. Okay, so this is also kind of peculiar. Now we will go to virtual memory. Before that, let us touch upon something which is happens on write misses. Okay. Till now, the way I have described the cache, I have described everything as if a search for a piece of information is happening in the cache, whether it is there or not. Okay. If it is there, it is returned to the CPU immediately, to the actual execution part of the CPU immediately. If not, there is a miss, and what to do if there is a miss, etc. There is also another alternative, not an alternative, but another thing that you have to consider. There is also a possibility of a write miss. A write miss is slightly more complicated to visualize. A write miss is not about I require a data to execute. A write miss is that I want to perform a store operation now. I want to store information into memory. Now, I know that storing information into memory is as slow as reading information from memory. It is the same, it goes through the same memory bus. So of course it is slow. What to do in this scenario is the question. Okay. What to do? I have to first check whether there is now a reverse translation. Okay, so earlier I was trying to decide that whether the information I need is there in the cache or not. Here also I have to take a same decision, but I am looking outward towards the memory. So what I mean by that is, if you look at the direct map cache data, when you are looking outwards, okay. Now from the cache, earlier we were looking from the memory to the cache, whether it is how many can clash. Here also there is an issue of many to one mapping, but I am looking away from the cache towards the memory. Okay, and I am trying to see whether the cache block that is currently there, is it actually the memory block where I want to write the intended thing. If not, it is a miss. So here among these blue colored blocks, 4 blocks are possible. Suppose I want to write to block 00101 in main memory. However, it is actually currently, so I have to check which among these 00101, 01101, 10101 and 1100101 is actually present here. Okay. Among these, which one is actually present? First I will check. If it is present, I will say it is a write hit, and I will update the cache by updating this block on the cache. If that is not there, it will be called a write miss. Okay. Now, what to do if there is a write hit? There are 2 options. What to do if there is a write miss? There are 2 options. Among these 2 into 2, 4 options, in practice, only 2 options are popular. Among these 4 combinations, okay, 2 options are popular. I will come to them. First, I want an answer from you. First, consider write hit, which means that I am trying to write some data into a particular memory module. I first check the cache, whether the block to which I am trying to write the data in memory is present in the cache or not. I find yes, it is present. So it is write hit. And I update that block. Remember, I will probably update only one word in the block. My SW instruction cannot deal with blocks, it deals with one word at a time. So I update one word in the cache. Do you think that is the end of the story, or does this create any problem? Any student wants to answer? What complication it creates?
Sir, when we get a read request for another one which is mapped to the same block address, then the original value will be lost since the value in memory was never rewritten.
Correct. No, yeah, you are actually coming. Yeah, your answer is correct, but it is a more advanced answer. I want an answer which, first of all, so what you are inherently assuming is that I will update the value in the cache block, but I will not update the value in the memory block. Is that what you are assuming?
Yes, sir. Like when we need a refresh of the cache, because at that the
Yes. Yeah, I cannot hear you, Preet Kumar. Yeah.
Hello, sir.
Yes. Now I can hear you. Yes. Yeah. Tell me. I don't know whether it is an issue with my system or I cannot.
Hello,
Anyways.
sir.
Yes. Now, yeah. Can you please quickly again tell what you
so
were
sir,
answering?
when we have a read miss for the same block address.
Yes. So that
we,
another block will come and overwrite it. So the content will be lost. That's what you're saying, right?
Yes, sir. Yes, sir.
Which means your inherent assumption is that the value would only be updated into the cache without a synchronization into the memory. Is that your inherent assumption?
Yes, sir.
No. That, yeah, your assumption is correct, but that is only one of the options. Right. What you have assumed is called a write back policy. The answer is very good, very intelligent answer, but there can be two policies when a write hit happens. If a write hit happens, the more intelligent and more efficient but more complicated option is what Preet Kumar just mentioned. You update the value in cache, but do not perform the corresponding update into the memory. So you kind of now intentionally have a desynchronized cache and memory block. Why did you do that? Well, you did that because, you know, syncing it into memory, it will take 100 clock cycles. Okay. So will you wait for 100 clock cycles unnecessarily? What is the hurry? I mean, why do you need to, you know that there will be no direct access to memory from processor. Any access to memory from processor will happen through cache. So when the cache is getting read, and again that blue block is exact, I mean, again the next memory access is actually the same block of memory in the cache, you have no problem. You have updated that block, return that value to processor. The problem happens is what he mentioned, that now suppose a necessity comes that this blue block in cache have to be replaced by one of the three other blue blocks in memory. Now this is a problem, because if you suddenly replace it with something in memory, it will overwrite the change that you have made. You have not yet committed it to main memory. So at this situation, you now decide that, okay, now let me keep it. Now let me first synchronize it into the main memory, then I will update that block. This is called a write back policy. And now you need to remember that the block which is there in the cache has been edited but the edit has not been synchronized with the block in memory, corresponding block in memory. For example, if currently block 00101 is mapped to the cache and the cache block has been modified, suppose after some time a necessity comes that 01101 block has to be brought in the cache, the 00101 block in memory must first be synchronized with the content of the cache, then the cache block can be overwritten with 01101 block. So you must remember this, that this cache block has been edited but has not been synchronized. And block which has been edited in cache but has not been synchronized with memory is called a dirty block. And in such a case, you have to maintain another extra bit called a dirty bit corresponding to every cache block. So now you had this valid bit, now another dirty bit has to be kind of maintained for every cache block. So you had the tag, other than the main data, you had the tag is an overhead, the valid bit was an overhead, and now this dirty bit comes, which is a further overhead for every cache block. However, how does it help? It helps because every modification you make to the cache, you do not need to go into the main memory and modify. The alternative is just the simplified option I just mentioned. You say, no, I do not want to go into this type of more complication that I have to remember what is a dirty block and what is a clean block and etc. Any write I perform into the cache, immediately I will synchronize it to memory. Such a policy is called a write through policy. Okay, so there are two options. One is called write through, and another is called a write back. Okay, of course, write back is more complicated. Write through can be optimized a little bit by having a further write buffer, okay, into the microprocessor beyond the cache and in between the before going out to the bus, where you kind of push data to waiting to be written into the cache, and you do not wait when the writing to cache completes or not. Writing to memory completes or not, you start executing other instructions and say, okay, let that write to the memory happen in the background, because anyway it is going to take hundreds of clock cycles. So this is called a write buffer. That is an hardware mechanism that is implemented. Okay. Write through can make writes very long, because if the CPI is 1 and if the write to memory takes 100 clock cycles and only 10% of instructions are stores, because there is a mandatory write without write buffers, it can be really bad, because if the mandatory writing to memory happens for every store, then your effective CPI can become 11, which means effectively with only 10% stored instructions. Okay, it is so bad that effectively you are executing only one instruction per 11 clock cycles, whereas ideally you had to execute one instruction per clock cycle. Okay, so thank you for the answer. Now, what happens if there is a write miss? There are further two options. One is called write allocate and write no allocate. I will now project some other flowchart diagram to explain what are these two options. Okay. Wait. First, let me describe write through. Write through with write allocate is with no write through with no write allocate is one of the common options, and write back with write allocate is the other common option. Okay, what is write allocate? I will describe. First of all, this is write through. Okay, how is it write through? You have to look at the write mechanisms, and you have to look at what happens when there is a write heat, a write miss, a write heat. If there is a write heat, this takes a lot of time. This arrow, I mean, this is hundreds of clock cycles. What happens if there is a cache write miss? What is cache write miss? I do not have the block corresponding to memory in my cache. Then write no write allocate performs something drastically, which is shocking. It does not perform the write or update into the cache at all. It only performs the update into the lower memory blocks, maybe using write buffers or something. Think about it. This is like shockingly against the principle of cache. The principle of cache says that all read write should happen through cache. Here, you look in the cache. I want to write some data in the cache block. Is the block corresponding to the one where I want to write the data in memory? Is it there in the cache? If it is yes, I update the cache block and I immediately update it into memory. That is not very efficient, but this up to, I mean, this is philosophically satisfying that okay, yeah, it is performing like what it is supposed to do. It is synchronizing the cache with the memory. If there is a write miss, on the other hand, it does not even care to synchronize cache with memory at all. It just directly goes into memory and updates. Now you might say, what is this? I mean, come on, this is, I mean, intentionally you are desynchronizing the cache and memory. I mean, what is this? Well, and this is not even a dirty concept. The dirty bit concept comes when you have modified the cache and you have kept a record that this has to be later modified to memory. Okay, this is not a dirty bit concept. You are not at all modifying the cache. You are directly going into memory. This can be useful when the processor is performing a lot of writes to IO buffers which are memory mapped. We studied memory mapped IO in one of the classes. I will again cover it maybe tomorrow, maybe on Thursday as a refresher because most students were absent. IO devices in modern computers are often mapped to special memory locations, and writing and reading data from them happen through memory accesses. Okay, portions of memory are mapped to these devices, and they are from there reading and writing can happen. Okay, so this can be useful if the processor wants to write a lot of data to the IO devices into the memory without hoping to again reuse it back or reading it back. It's just outward write of data. So that is fine. You don't bother about the cache. You just keep on writing to memory. Okay. Remember, these devices, IO devices, do not access the cache. They only access the memory. Okay. So this is shockingly against the basic principle of hierarchical memory design, but this is one of the options which is actually implemented. Now, what happens if there is a read? The read is more easy to understand in a write through with no allocate. I mean, if there is a cache hit, you immediately return the data. Otherwise, you locate a cache block to use read data from it. So there is a miss and you return the data. So there is nothing extraordinary. So this combination of write through on write hit and no write allocate on write miss is one combination. The second combination that is common is write back with write allocate. Write back when write hit, write allocate with when write miss. Let us come to it. Okay. First of all, here the writing mechanism. Let us look at the writing mechanism. If it is a cache hit, I update the cache into the memory cache block, but I do not update it into main memory. So that is why it is a write back scheme. But I keep a record that the cache block is dirty. Secondly, if there is a write miss, I look at where I want to have the hit. Is it dirty? Yes, it is dirty. If it is dirty, I synchronize it with the downward, memory below it, to main memory. And then you read the data from lower memory into the cache block. Why is this red marked? I will upload this into on Moodle. And there are some comments written here. You download this file and have a look at the comments. So you read data from memory into the lower cache block. It is overwriting is fine because you have taken care to write the dirty block into the lower memory. If it is not dirty, you don't care. You just overwriting. Okay. And then you perform the write into the cache block. Why did you require to read the corresponding block of memory into the cache block and then perform the write? Because your writing will be through SW instructions which deals with one word at a time, whereas your block is possibly a combination of multiple words. So first you fetch the entire word into the cache, then you update maybe only one word in the cache, and then if there are further SW instructions directed into the same cache block, you will keep on updating it. Okay, and you mark the cache block as dirty after performing the write. What happens if there is a read hit miss mechanism? If there is a read hit, no problem, immediately return the data. This happens within one clock cycle. If there is a miss, first you locate which cache block to use. Is it dirty? If it is dirty, you cannot just bring the data from memory into the cache. Okay. You first write the previous lower data to main memory. That is the situation that Preet Kumar was mentioning. Okay, that first you cannot just directly, if you directly read in data and replace that block from memory, the changes will be overwritten. That cannot be allowed. So you first synchronize with the lower memory, just as you synchronized when there was a write miss and there was a dirty block. Synchronize with lower memory and then you read the cache from lower memory. You mark the cache block as not dirty because no write operation has been performed on the block. But if it is not dirty, you don't care. You just read in data, overwrite it by bringing in a block from lower memory. Okay, finally you return the data. So do you understand what was going on? Any questions about this write hit, write miss policies? There are two write hit policies, write back and write through. There are two write miss policies, write with allocate and write with no allocate. They are combined into write back with write allocate and write through with write allocate. Why are they combined like this? Well, my guess is they are combined like this because in write through, this not very clever immediate synchronization with memory takes up lots of clock cycles, but it performs some saving when there is a cache miss. It only writes data to the lower block without waiting, and probably there are write buffers available, so it doesn't spend much time caring about to update the cache. So this side incurs lot of overhead, but this does not incur any overhead. In the write back with write allocate, this does not incur much overhead. Okay. Uh, uh, when it is not a dirty block, okay, this sorry, when there is a dirty block, it incurs overhead in both read and write. Okay, but it does not immediately perform a mandatory write into the lower block of memory. So there it saves some clock. It's a balance between these two schemes. In both of these two schemes, they have their pros and cons. However, if you look at the write through with write allocate and you look at this write, what happens when there is a write he miss, this portion of the diagram, okay, this portion of the diagram is shocking actually. I mean, this is completely against the principle of memory hierarchy. But anyways, this is an option that is actually followed.
Sir, I had a question.
Yes.
In write back with write allocate, the first diagram.
Okay.
When there is a read miss and the block is dirty, that means the cache and the memory has not been synchronized, but cache has the latest data, right?
Yes.
But
You mean
why-
this part that I am highlighting?
Yes. So why do we need to write it back? Because we are reading it, right? So we read the latest
You
data.
are reading what? You are
Read
reading which block?
a block which is dirty. That means
No, you are not reading the block which is dirty.
I'm reading a word from.
There has been a cache miss. Heat has followed no.
Oh, okay. Sorry. Yeah.
This is a very important good question. This actually confuses a lot of students, and even when I was a student, I studied this scheme for first time, it confused me. When you have come in this portion of the diagram because you do not have the block you need into cache. It is a completely different block from the one that is sitting there in the cache in the location. First, that has to be evicted. It has to be kicked out and your block that you need has to be brought in. Question is, before you kick it out, you check. I am kicking it out, but did I synchronize its contents with memory? Is it dirty or not? If I did not synchronize, it is dirty. So if it is dirty, I follow this yes path and I synchronize it into memory and I override that cache block with not the same block, with some different block. So again, let me go back to the slide and display. Look at this direct map cache scheme. Consider a write back scheme. Suppose you currently have block 00101 is in memory is mapped to cache index 101. You have performed some writes into this block locally in the cache. Because it is a write back policy, you were lazy and you did not synchronize it with the 00101 block in memory. And you have marked the block at index 101 as dirty as a result because it is not synchronized. Now, after some time, this is a direct map cache. After some time, the program wants memory block 01101 into the same. It wants memory block 01101. What to do? This is a direct map cache. No option. 01101 must come in and evict block 00101 in the same location 101 in the cache. So you look at that block before evicting it. Is it dirty? Can I directly take 01101 and push it to the cache? That will overwrite the content. Before such overwriting, you check whether it is dirty or not. If it is dirty, you synchronize this with 00101. So now cache and these are synchronized. And now you say, okay, fine, I have synchronized my cache block with the one in memory. Now I can overwrite it with 01101 and bring it to the cache. Is it clear now, students?
Yes, sir.
Good question. Thank you. In fact, that is kind of something that is actually written in the comments. That is what I have written in the highlighted part. If you have a look at the comments, you will find. I will upload that, upload the slides and this thing in on Moodle. This is exactly what I had written. So these are very, very interesting topics. Okay, I mean, actually, many of you do not would probably not be working on computer architecture, but this is something which is which are extremely interesting, and this cache architectures, cache schemes, there are more advanced topics on cache also, which if you take HPCA you will study, especially what happens, how do you maintain synchronization between a cache and memory, or say local caches and a shared large cache in multi-core processors. In multi-core processors, the level 1 cache, the cache closest to the processor, is local to every core. So every core has its own L1 cache. But the second level or third level caches might be shared across all the, suppose there are 4 cores in your chip, on your CPU chip, on your microprocessor chip. All 4 are sharing the same cache. Now suppose there is some shared variable among different threads running on 4 different cores. So one of the cores has performed a local update to the variable in its local cache. Will that need to be immediately synchronized to the cache below it? Because if you do not, you have to take a decision. Because if you do not do it, the other core thread might want to access that value from the shared cache because it does not have that value in memory, and it will get an old value, a non-updated value inside it. So all these decisions have to be taken. How do you maintain coherence? How do you tell globally? How do you declare to all the cores that look, do not trust the value that is there on the shared cache because currently it is being updated. Okay, let the update complete and then you take it, or you stop multiple writes to the same cache location on the shared cache. All these things have to be figured out. So these are very, very, very interesting concepts. All of these are implemented in pure hardware. Okay, and the hardware that implements them are like super complicated because you can see these are not like, these are kind of difficult control decisions that you need to make in a very short interval of time. Current microprocessors run at multiple gigahertz clock speed. So you might find, I mean, very common to find a microprocessor with a clock speed of 3 gigahertz or 4 gigahertz. Say. So you have 0.25 nanosecond to complete the execution of one instruction. If there is a cache hit, you have promised to the programmer that if there is a cache hit, you will not incur any latency. Which means that you, to keep your promise, you must perform the cache search, returning the value from the cache, loading it to the target register of the CPU, everything within 0.25 nanosecond. It's not easy to design circuits like this. Very, very difficult. Okay. Forget about the transistor level design. Just coming out with the architecture of such circuits itself is very, very difficult. Okay. So, yeah, okay, thank you. we will continue with virtual memory, which is the next level of memory hierarchy, which will show the interaction between the main memory and your hard disk. Till now, we have considered a memory hierarchy where we were considering the interaction between the CPU cache and main memory. Now we will go further and extend the similar concept to main memory and your CPU or your hard disk. Okay. Thank you very much.